So hi, this is Mr. Dressen, and today I'm going to teach you about ideal gases. This is chapter 14.3 of your textbook. And remember, we did a little bit of talk early on from chapter 13.1 about the difference between real and ideal gases and some of the assumptions we make in order to call gases ideal. And so your learning objectives for the day are we're going to learn a little bit more about Avogadro's law, sort of an extension of it. This is more of sort of a background and basically how that led to the concept of a standard temperature and pressure, and that led to that molar volume of gas. That is a review. So how many of you remember what the molar volume of an ideal gas is? It's a special number. I'll give you 3 seconds, 4 seconds to blurt it out. Yes, the number is 22.4 liters per mole. And then finally we're going to learn a real important equation that allows us to solve a lot of problems when we're dealing with gases and reactions. And it's really the culmination of everything that we've learned about gas laws and the combined gas law. It's something called the ideal gas law, and that's really the most important thing that you're going to learn today. So we're going to go back and talk about Avogadro's law, and we know that Avogadro's law led to this special number, which was 6.02 times 10 to the 23rd molecules or atoms per mole. But really, originally what Avogadro talked about was that if you had equal volumes of gases, he made the proposition that if you have any equal volume of gases, they'll contain equal numbers of molecules. And of course, later on, we decided to call a large group of molecules moles. But he basically said, hey, if you have a gas that's 2 liters and another gas that's way different, but there's 2 liters of it, there'll be the same number of molecules at a constant temperature and pressure, and that was true for any gas. And so he basically just said they're always proportional. So this equation here, V over N, which equals K, is just sort of saying that volume over the number of moles, or in this case maybe the molecules, doesn't matter, equals some constant K, okay? And we'll talk a little bit what that constant K becomes, but it's really not important. In fact, this equation is not important other than the fact that Avogadro was able to graph and make graphs of volume versus molecules for different things, and was able to pretty much prove that gases follow his law. And basically, when you take this to its final resting spot, you get the volume of a gas at standard temperature and pressure. And so according to Avogadro's law, 1 mole of any gas will occupy the same volume as 1 mole of any other gas at the same temperature and pressure. And so what we need to realize is that if you are at 1 atmosphere, if you're at 1 atmosphere, and you're at 273 degrees Kelvin, which of course is 0 degrees centigrade, and if you have 1 mole of the gas, you're going to fill up a container to exactly 22.4 liters. Okay, now this is review. We've talked about this before, but that's the molar volume. Now what's going to happen, we've used that number steadily, but now once we learn the ideal gas law, that number will change depending upon, basically depending on whether we change temperature, or whether we change the pressure, or whether even we change the amount of the gas involved, okay? So again, take your time, write these notes down. The part in the green area is really important, that at 1 atmosphere and 273 Kelvin, the volume of 1 mole of gas is 22.4 liters. So make sure you get those notes. Okay, let's move on. So I've shown you this slide before, or this picture, and these are 3 different gases: argon, oxygen, and nitrogen. And really the only reason I show them to you is that if I got a mole of each one of these gases, argon, oxygen, nitrogen, and I had them both at the same temperature, which would be, in this case, 273, if I had them both at the same temperature and then I had them both at the same pressure. I mean, all three of them at the same pressure, and I actually went and filled them both, all of the three of them up to 22.4 liters. I would exactly have a mole of each gas. They would look the same, so everything about them would be the same volume, same pressure, same temperature, same amount of molecules. The only thing that would be different is that their masses would be different. And even in the vinegar carbon dioxide lab, we saw this when some of you filled up the balloon with carbon dioxide. Some of you made a note that it seemed like it was a bit heavier than a regular balloon. That's because carbon dioxide weighs 44 grams per mole. It's even a little bit heavier than argon. And air weighs somewhere between 28 and 32 grams per mole. And so you would have noticed a difference in the actual mass of the balloons, other than the fact that they were the same. So this is really, this slide is really the consequence of Avogadro's law. Here there's really no need to take detailed notes of any of this, other than to just sort of realize this concept that molar volume will be the same at the same temperatures, but the mass would be different. Okay, so this really is sort of the all-important slide. This is the ideal gas law. The ideal gas law, everybody, we just say Pivnert. So can everyone say that? Pivnert. Once more, Pivnert. And it is pressure times volume equals the number of moles of the gas times something new. Now, we've never seen this before, this big letter R, and then temperature. So we've all seen pressure, volume. We've dealt with temperature so far in this unit. We dealt with moles in chapter 12, but now we have a new value known as R. So generally speaking, when we set these problems up, we'd like the pressure to be in ATMs. We'd like the volume to be in liters. We'd like N just to be the number of moles, temperature to be in kelvins, and then that will give us a certain number for something that is known as R, the universal gas constant. And when it says universal gas constant, it means the universe. Not the solar system, not the galaxy, the universe. This value of R, which we could actually calculate in the lab, is a constant throughout the universe, just like the speed of light or anything like that. Okay? So make sure you take good notes on this, that you have this equation, PV equals nRT, pressure, volume, number of moles, universal gas constant, and the temperature in Kelvin. And as you can imagine, there's five different numbers here in the equation. However, one of the numbers, R, is always the same. So pressure, volume, moles, and temperature are what could possibly change. Usually a problem will give you three of those four, and you will solve for the other one using simple algebra. Now this equation, this slide is just a little different. It's actually, believe it or not, a derivation of how R is actually calculated, so how we get R. So it turns out that if you just use the equation PV equals nRT, and so you take our STP conditions, which is pressure is 1 atm, volume is 22.4 liters, we say we have a mole of gas, and then if we add in the temperature, we put in 273 Kelvin. These are all the things that we have identified as standard temperature and pressure. When we do that, we actually can calculate a value of R. And that's what I've done here. So what I've done is I've rearranged the equation to be PV equals N over T with R on the other side. So I have 1 times 22.4, and on the bottom I put 1 mole over 273. Obviously the ones cancel, so if you just take the molar volume, 22.4, and you divide it by Kelvin, 273, you basically get a value for R. And this value, no matter what, so for instance, if you change the volume in the above equation, what will happen is the pressure will change and maybe the number of moles, but as you change those four numbers up top, they'll always move around, but the value of R will never change. So basically, R sort of sits at the end of this equation. It never really changes, and the other four variables will change, but R stays the same. But this is one way to calculate R. Okay, I'll give you about 10 seconds to write this down. This is not necessarily something that I'm going to ask you on a test or anything, but I just want you to sort of see how you could rearrange this equation to calculate for R. For the rest of the problems we have, okay, you'll basically be able to use the R value and use it in the equation. But if you look here, what we did was we took nRT, we divided both sides by NT, and we ended up canceling out the nitrogens, canceling out the temperature. So R equals PV over NT, and that's basically what we have down here. Okay? So here is the actual value for R, the universal gas constant. R equals 0.0821 liters times atmosphere divided by moles times K. So it has this really crazy units. However, what I'd like to say about this is if you can ever get all of your, whenever you're trying to solve a problem, if you can get your volume in liters, your pressure in atmospheres, your N will always be in moles, and then you get degrees Kelvin. If you can get those four units for your P, your V, your N, and your T, then when you do the math, all of those units will cancel and leave you with what's left that you want, and so you could always use 0.0821. And then R also can equal 8.314 joules per mole K, and joules can also be kilopascals per mole K. But my general rule of thumb is we should really try to always get our pressure into atmospheres. If we do that, if we get everything into atmospheres, then we can always just use this value for R, which is 0.0821. This is a number I'd like you to memorize. However, I believe on the tests it'll actually give you that number. It'll give you the universal gas constant. Okay, and so if you start working these problems and you keep track of your units, you'll see that all those units cancel when you use the problem. So again, 0.0821, we'll like to use that probably 80 to 90% of the time, and then the other times we might end up using the 8.314 number. So here's an actual problem to solve, and so here's a typical ideal gas law problem. It says calculate the pressure in atmospheres, okay, so our unit will be an ATM, of 0.412 moles of helium at 16 degrees Celsius occupying 3.25 liter. So if you look through there, you see we pretty much have everything that we need. And so if you look over here, just write down what's given. Pressure is X, and it's going to be an ATM. N equals 0.412. Temperature, I've actually taken 16 and I added 273 to give me 289 Kelvin. Volume is fine, it's in liters, okay, 3.25 liters. And then R, I can now use the 0.0821 liters per 8 times ATM divided by mole K number. Volumes, a common mistake with these problems is to not put your volumes into liters, but to leave them in milliliters. Try to put them into liters, and then that way you can use the appropriate value of R. Okay, so go ahead and write down these givens, okay? Okay, now I think I'm going to give you like a couple of minutes, 2 minutes. I'll watch my clock here on the presentation recording to try to solve this problem. 2 minutes. So go. Try to work the problem in your notes. So if you're stuck, remember the equation. P V equals nRT. And then remember that you're looking for pressure, and so you want to get that on one side, so you divide by V, divided by V. So it looks like pressure is going to equal nRT over V. Okay? And I've actually done these problems a lot over the years whenever I work with gases, so I actually know all the permutations of like setting these equal to each other. So I know P equals nRT over V, I know V equals nRT over P, I know, temperature equals PV over nR. I sort of know all these permutations. So you want to solve for this. You got about 1 minute to go. Okay, you have 30 seconds. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, stop. So here's my solution. This is my, on a PowerPoint type solution, so I don't have it quite set up the way I did before, but I've plugged all the numbers in. And so if you take 0.412, 0.0821, and 289, you multiply them by each other and divide by 3.25. The answer you should have gotten was right around 3 atmospheres, 3.01 atmospheres. So basically, if you know the amount of gas and you know your other conditions, you could calculate the pressure on the inside. Now next week, you're going to be doing a lab. Hopefully, you'll either do a lab or maybe an activity with Miss Page where you'll actually be able to do similar calculation to figure out the pressure inside when a popcorn kernel pops. We'll see how that goes. So I'll leave this up here for about 10-15 more seconds so you can write that down. But again, if you can get your volume in liters, and you always have to get that into Kelvin, you need to be in Kelvin again, and then you just have the moles, then you can use the 0.0821 number and calculate your pressure in atmospheres. I think one thing you might start thinking about is when you see this moles here, think about how else could they ask a problem like this. For instance, they might not ask you the moles, they might in the problem give you the grams of the compound, and then you may have to convert it to moles to solve this ideal gas law problem, which goes back to chapter 12 and is one of the reasons I said, remember, we may always be using the mole city map. So you may be given grams of a compound to go to moles. So keep that in mind. Okay, so I do have a cool down for you to work. You can put it in your logs if you want. Go ahead and take those out. It's just a cool down. I'm not sure how much time is left in class, but you can do this cool down, and then there will be some ideal gas law problems for you to do as well. So here's the cool down. So go ahead and write that down. It's basically what pressure is exerted by 0.450 mole of a gas at 25 degrees Celsius if the gas is in a 0.650 liter container. So this problem is pretty similar to what you did in the last problem, but see if you can solve it. Okay, so I'll again give you a little bit of time to work this problem. I might see if I can work it a little bit with you. I think that this is probably, since we're talking about the ideal gas law, it must be a PV equals nRT. Okay. And it says what pressure? So it looks like it's over volume again. So it looks like nRT over V, 0.450 times 0.0821. Oops, times I ran out of room. But maybe I would realize that the temperature would go in here in Kelvin. And then I guess I'd put that over 0.650 liters. Keep in mind that if you wrote 650 milliliters, your answer would be wrong because the number 0.0821 wouldn't work anymore. You'd have to change that by a factor as well. Okay. So I'll give you about 1 more minute, and then I'll show you the answer. You got about 30 seconds. Okay. And the answer is 16.9 atmospheres is the answer. So I hope you've enjoyed learning about the ideal gas law today, and I hope this helps you solve some of these problems as we move forward. Thank you very much.